In this lesson, we're going to look at derivatives of algebraic functions. The first thing that we're going to look at are some of the properties of derivatives. The first property is that if I take the derivative of any constant, it's going to be 0. Because think about what the derivative represents. It represents the slope of the tangent line for that function at a point. Well, if I have a constant as my function, that means that I have a horizontal line. Well, the tangent to any horizontal line is going to have a 0 slope. So that's why having the derivative of a constant equals 0 should make sense if we think about it as the slope of the tangent line. If I have multiple functions being added or subtracted, and I want to take the derivative of that sum or difference, I could take the derivative of each individual function. If I have a constant times a function, we could take the derivative of that function and multiply it by the same constant. And lastly is if I have a function written as a power function, so x to the n, the way that I could take the derivative without having to find the limit of the difference quotient is by dropping the exponent down to become a coefficient and then lowering the current exponent by 1. This only works when my value of n is a real number. So as long as my exponent is a real number, so that's any rational or irrational number, so that includes your integers, that includes your whole numbers, that includes any fractions or decimals, then we're allowed to use this rule. Let's first look at an example where we're going to rewrite different functions as power functions. So first I have 1 over x. So remember, when x is in the denominator of the fraction, that means my exponent is negative. So we can rewrite this as x to the negative 1. Right below it, we have the square root of x. And then you also see another radical, the cube root of x to the 5th. So remember, if I have a radical where n is my index, and then I have an m exponent also on the variable, it can be rewritten as a rational exponent. So x to the m over n. That means the square root of x can be rewritten as x to the 1/2. The cube root of x to the 5th can be rewritten as x to the 5/3. And lastly, like I said, as long as the exponent is a real number, so any fraction, any decimal, any whole number or integer, we can rewrite it as this power function. So this is 5x to the negative 7.1. Now let's use these properties in order to find the derivative of f. So in my first example, I have x cubed minus 5. So I notice that I have two different types of functions that are being subtracted here. I have x cubed, and then I have negative 5. So I can take the derivative of each term individually. So the derivative of x cubed, well, that's a power function. Remember that if I want to take the derivative of a power function, that's nx to the n minus 1. So the derivative of x cubed, so f prime of x, is equal to 3x squared. Next, I have that negative 5 term. Again, the derivative of any constant is always 0. So really, this is 3x squared plus 0, but we know we don't have to put that plus 0 in there. So there's the derivative of x cubed minus 5. In the second example, I have 5x to the 11th power. If you remember from our properties, if I have the derivative of a constant times a function, we take the derivative of the function like we normally would and multiply that with a constant. So here I have 5x to the 11th. Well, the derivative of x to the 11th is 11x to the 10th. But now I'm multiplying that with the constant 5 that I already had. So when I simplify, it's 55x to the 10th. And in this third example, I have a mixture of different types of functions. So I have a polynomial that has degree 5 term, a degree 2 term, and a constant term. Just like before, I'm going to take the derivative of each term individually. So f prime of x is equal to 2 times 5, so that's 10x to the 4th, lowering my exponent by 1, minus 7 times 2 is 14. 2 minus 1, that lowers my exponent down to 1, so that's negative 14x, plus 4, well, that's just a constant, that's going to be 0. So my derivative is 10x to the 4th minus 14x. Okay, so some different types of functions. So I have the 4th root of x. The first thing that I would want to do is rewrite that as x to the 1/4. And now I can use my power rule. So f prime of x is 1/4. X to the 1/4 minus 1 is negative 3/4. And you could just leave it like that. There's no need to rewrite it with a positive exponent or rewriting it using a radical sign. I would just leave the answer like that. I think that's perfectly fine. In the second example here, we see that we have a quotient. So the first thing that I always want to try to do when I have a quotient, and the same thing will be true in the next example with a product, is I want to simplify the expression. So remember, we can simplify this by separating the fraction. So I have 17x cubed over x squared minus x over x squared. And now I just use my properties of exponents to simplify it. So f of x is now 17x minus 1 over x. And 1 over x we already talked about is really x to the negative 1. So you can even rewrite that from the start. So my derivative here is 17 plus x to the negative 2. In my last example, like I said, I have a product. So if I can, I want to try to simplify my product. So I'm going to distribute that 5x to the 4th. So my new f of x function is 5x to the 6th minus 35x to the 4th. Now I can use my power rule. F prime of x is 30x to the 5th minus 140x to the 3rd. So just to review once more our properties of derivatives, if I'm trying to take the derivative of any constant, it's going to be 0. So if I have the derivative of 7, it's automatically 0 because again, if I have a function that's 7, that means I have a horizontal line. The slope of the horizontal line is always 0. So any tangent to a horizontal line will also be horizontal and its slope will also be 0. If I have the sum or difference of multiple functions, I just take the derivative of each one of those functions. So if I have something like x squared minus 5, I'm going to take the derivative of x squared, which is 2x, and then take the derivative of -5, which is 0. If I have the derivative of a constant times a function, I still take the derivative of that function and then multiply it with the constant. So if I have the derivative of 7x cubed, well, the derivative of x cubed is 3x squared. I'm still going to multiply that with 7, so 21x squared. And lastly, we have our power rule, which we've been using the last few examples. If I have a function written as a power function, I can take the derivative without using the limit of the difference quotient by taking this little shortcut. You drop the exponent down, decrease the current exponent by 1.